Find the shortest route which passes through all 14 major cities and returns to the first city. The traveling salesman problem is one of the most intensely studied problems in computational mathematics, and we'll solve this problem using genetic algorithms. The 14 major cities include Madrid, Barcelona, Paris, London, Amsterdam, Oslo, Berlin, Vienna, Rome, Athens, Istanbul, Kiev, Moscow, and St. Petersburg. The distances used in this problem will be straight line distances in units of kilometers. We'll begin by measuring out the distances between each combination of two cities. For example, Barcelona and Rome are separated by a distance of 844 kilometers. Amsterdam and Athens are separated by 2,167 kilometers, and Berlin and Kiev are separated by 1,201 kilometers. After the distances between all 91 pairs are measured, the values are entered into a table. Only a portion of the table is shown here. For this genetic algorithm, we'll use 64 species per generation. The fitness equation for species I will equal the distance of the longest route, or species, in that generation minus the distance from the route taken by species I divided by 1,000 raised to the fourth power. This fitness equation favors the shorter routes and ensures all species have a chance to reproduce, except the species with the single longest route. In this algorithm, we'll use a crossover probability of 5%, a mutation probability of 0%, an elitist model to preserve the single most fit species. This will ensure that the minimum route between successive generations will not increase. The algorithm will terminate once the average route is less than 500 kilometers more than the minimum route. The parameters shown here were simply made up based on intuition and judgment, and after experimenting with the algorithm. It is not uncommon for the modeler to tweak these parameters to improve performance. The algorithm will begin with 64 species, each with a randomly generated route of the 14 major cities. Here is a portion of the table of randomly generated routes, which will be used for the first generation. If we plot the route of the first city on the map, we notice it is not the shortest route possible. One improvement would be to travel from Athens to Istanbul directly and stop through Vienna when traveling between Kiev and Barcelona. Currently, this route totals 22,109 kilometers. If the algorithm makes the suggested route revision, the total distance would reduce to 20,151 kilometers, but still be far from the shortest route. The only path between consecutive cities of this species route, which may be part of the optimal route, is the path between Istanbul, Turkey, and Kiev, Ukraine. Back to the tables, the algorithm computes the distances between consecutive cities on the route. For example, the straight line distance between Kiev, Ukraine and Barcelona, Spain is 2,383 kilometers. This distance of 2,383 kilometers was recorded in our tables of distances mentioned previously. Next, an additional table tracking the distances between cities is created. We can compute the distances for the remaining paths in the first route, as well as for all 64 routes, or 64 species. After the last column, an additional column is used to add all 14 paths, which equals the total route distance. From this first generation of 64 species, the average route distance equals 22,928 kilometers. The minimum route distance equals 17,917 kilometers. And the difference between these two distances equals 5,011 kilometers. Since the difference is greater than 500 kilometers, the termination criterion is not satisfied, and a new generation of species will be synthesized. Before we do, let's take a quick look at the map, comparing the difference between the average route, the minimum route, and the maximum route distances for the first generation. Species 43 has a total route distance of 22,931 kilometers, which is just 3 kilometers longer than the average route distance. Species 58 has a total route distance of 17,917 kilometers, which is the shortest route of the first generation. This species will have the highest fitness during reproduction. Species 25 has a total route distance of 26,681 kilometers, which is the longest route of the first generation and will have a fitness of 0. Now we'll perform crossover. For this particular problem, we cannot simply swap data between two species during crossover. Otherwise, we would likely end up with routes visiting certain cities twice and not visiting other cities altogether. This would be the case for City F, Kiev, because it is in Route 1 twice and not in Route 2 at all. Therefore, we'll modify the crossover step such that two cities will switch their order within the same route, or species. This would ensure all cities will still be visited exactly one time. From the algorithm parameters, the probability any single city in any single route will be crossed with another city in the same route is 5%. This example of modifying the crossover step is sometimes necessary in genetic algorithms in order to fit the problem's constraints. After the crossover modification, reproduction is more similar to mitosis than meiosis. Next, the distances that were affected from the crossover operation are recalculated. Now we're ready to calculate the fitness values and normalized fitness values of each species. The equation for fitness was defined as the maximum route distance of all species in that generation minus the route distance of the species being considered divided by 1,000 raised to the 4th power. Where the maximum route distance in the first generation after crossover is still 26,681 kilometers. Plugging in the distance for the first species and the maximum distance, the integer fitness for the first species equals 528. The fitness is calculated for the second species and equals 81. After the remaining fitness values are calculated, it's time to calculate the normalized fitness values, which equal the fitness value of the given species, I, divided by the sum of the fitness values for all 64 species in the generation. These normalized fitness values represent the probability that a specific species will be chosen as one of the 64 species in the following generation. For example, if we take a closer look at species 1, which has a normalized fitness value of 0.0143, the probability of an event F occurring R times given n opportunities is shown, where n equals the number of new species to be selected for the next generation, 63, R equals the number of times that particular species is selected in n opportunities, and P equals the normalized fitness value. In this formulation, n equals 63 instead of 64 because we're using an elitist model, which guarantees the survival of the most fit species, one time in each generation. Next, we'll compute the probability f of r. As we vary the value of r from 0 to 5, we learn the probability of species 1 not surviving into the next generation is 40.4%. The probability species 1 will be selected into the next generation one time is 36.9%. The probability species 1 will be selected into the second generation 2 times is 16.6%, and so on. Familiarity with the binomial distribution is helpful when analyzing the algorithm and adjusting the parameters. Next, our second generation of species is created. As before, this table only shows the first 5 cities of the first 7 routes. One observation is that the first 5 cities of routes 3 and 4 are the same, which may suggest the distance between cities I, F, E, A, and K are close together. Indeed, Moscow, Kiev, and Istanbul are close, and Amsterdam and Paris are also close, but Istanbul and Amsterdam are not close. As it turns out, species 3 and 4 in the second generation are the same, and are reproductions of species 58, the elite species from the first generation, which had a fitness value of 5,921, a normalized fitness value of 0.1598, and a survival probability as shown, after factoring the species' elite status. Next, the distances for all 64 routes are calculated, and the termination criterion is tested. From the results, we learn species 52 has the shortest route of 16,478 kilometers, and the average route distance is 19,790 kilometers. Since the average route distance minus the minimum route distance is greater than 500 kilometers, we'll synthesize a third generation. To do so, crossover is again performed at the crossover probability of 5%. The affected distances are recalculated, and the fitness and normalized fitness values are calculated as before. Next, a third generation of species is produced. This process continues until the termination criterion is met. In this third generation, the average route distance is 17,785 kilometers, and the minimum route distance is 16,104 kilometers. The termination criterion is still not met. Results for generations 4 through 6 are shown here. We notice the average and minimum route distances continue to decrease. Generations 7 through 13 are shown here. Finally, in the 20th generation, the termination criterion is met. When plotted on the map, the minimum route found by the genetic algorithm is clearly an improvement from the previous results. The power of genetic algorithms is more pronounced for larger problems where there are thousands of nodes and links, rather than simply 14 nodes and links, where we could have guessed a near optimal solution just by viewing the map. This route by city letter is FIMJDNAGKHCLBE, and then back to F. This would be the same route distance irrespective of starting city or direction. When reviewing the possible solutions, the answer is B.